Hi everyone. Today we'll learn when local extrema are also absolute. In the first exercise, we're given two functions. The first one has a local minimum at x equal to 0. The second one has a local maximum at x equal to 0. Can we conclude that these local minima and maxima are also absolute? And can we use the first derivative to do that? If you would like to think about this problem on your own first, stop the video now. You can also download these notes using the link in the video description. The first function is the absolute value function. On the left side of 0, the function is decreasing, meaning its derivative is negative. On the right side of 0, the function is increasing, meaning its derivative is positive. Because the derivative changes sign from negative to positive, you get a local minimum. This local minimum must also be absolute, because this function always increases on the right side of 0. The derivative is always positive for x's greater than 0. And this function is always decreasing on the left side of 0. The derivative is always negative there. Similar situation happens in the second picture. The derivative goes from positive to negative at x equal to 0. What's more, the derivative is always positive on the left side of 0 and always negative on the right side of 0. The function is always increasing on the left side of 0 and always decreasing on the right side of 0, which tells you that the local maximum must also be absolute. Can we use the second derivative to make similar conclusions about these two functions? Both of these functions have a critical number x equal to 0. The first function has a local minimum there. The second function has a local maximum there. What does the second derivative tell us? In the first case, the first derivative is 2x. The second derivative is 2. This tells you that the second derivative is always positive, no matter what x you plug in, telling you that this function is always concave up. This function will never curve back down, which implies that this local minimum must also be absolute. In the second case, the first derivative is negative 4x to the third power, and the second derivative is negative 12x squared. When you plug in x's less than 0 to the second derivative, you get negative numbers. When you plug in x's bigger than 0 to the second derivative, you get second derivative negative, which means no matter what x you plug in, besides 0, which is the only exception, when you plug in x equal to 0 to the second derivative, you get 0, but everywhere else, this function must be concave down, meaning your local maximum must be absolute. What we just discovered are the first and second derivative tests for absolute extrema. The first derivative test says that if the derivative changes sign from negative to positive at a critical number, then you get a minimum. And because that derivative is less than 0 for all x's on the left side of c, and is greater than 0 for all the x's on the right side of c, the function is always decreasing and then always increasing, giving you absolute minimum. On the other hand, if the derivative goes from positive to negative, the function goes from increasing to decreasing, giving you a local max. But this first derivative is greater than 0 for all x's on the left side of c. So this function is always increasing on the left side of c, and this function is always decreasing on the right side of c, telling you that this maximum must be absolute. The second derivative test says that if you're given a critical number of a function f, given by the condition f prime of c equals 0, and if you know that the second derivative is continuous, then if the second derivative is always positive, that tells you that the function is always concave up, telling you that you get the absolute minimum there. And if the second derivative is always negative, then the function is always concave down, meaning you get the absolute maximum. And in the second derivative test, it's possible that the second derivative doesn't have to be positive or negative at c. that C is the only exception, the same way we saw it in this example in the top right corner. There is one more way to determine if a local maximum or a minimum is also absolute. Imagine you're given a continuous function with only one critical number. And let's assume that this critical number gives you a local maximum, just like in this picture. There is a critical number, x equal to 0, giving you a local maximum. Is it possible that this local maximum is not absolute? I believe this is not possible. If this function ever goes back up, it will have another critical number. If this function goes back up rapidly, then again, you will obtain another critical number. Because this function has only one critical number, x equal to 0, it's not possible for this function to go back up, which suggests that if a function has only one critical number, and that critical number gives you a local maximum or a local minimum, that local maximum or a local minimum must also be absolute. This is exactly what the next theorem says. If you're given a continuous function with only one critical number, then if you have a local maximum at that C, then you also have absolute maximum at that C. And if you have a local minimum at that C, you also have absolute minimum at that C. I should also mention that all these three theorems that I introduced in this video apply to functions not only defined everywhere, but also defined on an interval. In such cases, we obtain absolute maxima and minima on that interval. One more thing. Knowing when a local extremum is also absolute will be very useful to you when it comes to solving optimization problems. For optimization problems, you often need to know if a local extremum is also absolute, and we need to have tools to be able to determine if that local extremum is also absolute.